Thanks for your introduction. Hello everyone, I'm Lei Wang from China. My previous affiliation was in Gunting University, and most work was done there. So here I want to introduce my work during my stay in Gunting University. It's about aerosol-assisted atmospheric pressure plasma deposition for Cvelbar containing antibacterial coatings. In this talk, first I will briefly introduce antibacterial coatings. Secondly, I will show how aerosol-assisted atmospheric pressure plasma deposition was performed and the analysis were carried out for the deposited coatings. And thirdly, we will characterize the coatings on the surface morphology and chemical composition. And fourthly, we'll check the antibacterial effects and the cytotoxicity of coatings. And finally, the main conclusions will be given. Antibacterial coatings are functional coatings which can inhibit the growth of microorganisms or materials. Antibacterial coatings have many applications, such as medicine or healthcare, textiles, food package, indoor air quality. According to the market report, antibacterial coatings contributed to more than $100 million in the global market of last year, especially as we experienced the COVID-19, and there's a huge requirement for the antibacterial coatings and also antivirus coatings. Regarding the medical applications of antibacterial coatings, we can find some examples like wooden dressings, implants, and catheters. A typical example of antibacterial coatings is Cvelbar containing antibacterial coating, which has been widely used due to low antimicrobial resistance. However, it may have side effects of cytotoxicity due to overdosage. Therefore, controlled release of Cvelbar ions are necessary for biocompatible coatings, especially the combination of initial burst release and followed slow release, which can be beneficial for the medical applications. When antibacterial protection in early stage is required, and the long-term slow release is needed to prolong the lifetime of antibacterial coatings. There are many ways to produce Cvelbar containing coatings. Traditional chemical methods can produce desired coatings. However, it has disadvantages like high cost, hazardous chemicals, tedious multi-steps. Plasma-based method shows advantages over chemical methods by overcoming these drawbacks, like simple preparation, extraordinary versatility, economical, and sound-free deposition. Here, we would like to introduce the aerosol-assisted atmospheric pressure plasma deposition. In this talk, I will simply call this AAPPD. This technique can can deposit volatile or non-volatile precursor, while preserving the molecules of precursor in the aerosols from destruction in discharge. This technique paved the way to produce various functional coatings with core shell structure. In this work, we are going to apply this technique to synthesize Cvelbar containing antibacterial coatings, which hasn't been reported before. Now let's look at the experimental setup. It includes two atomizers to produce HMDSO and self-natural aerosol separately, as we see on the upper left figure. And all aerosols will be carried by helium gas into a DVD chamber. The discharge is driven by AC power supply at 24 kHz. In the beginning, we use several silicon wafers as substrates to study the influence of experimental conditions on coatings. The experimental conditions include continuous mode for sample B. As we see, the duty cycle is 100%, and pulse mode for sample E is 33% of duty cycle, and sample F with no cell nitrate in aerosol, and a control sample G with no aerosols. The treatment time in the experiment is 10 minutes, and the cell nitrate concentration is 100 millimole per liter. After deposition on silicon substrate, the coatings were analyzed with the same EDX, FTIR, XPS to study the morphology and the chemical composition. Accordingly, we optimized the experimental condition and further used PET fabrics as substrates in the deposition for biomedical applications. We checked Cvelbar and Leys with SAPMS. Antibacterial activity with gram-negative bacteria E. coli and gram-positive bacteria S. aureus. We also checked the cytotoxicity with murine fibroblast cells. Now let's look at the same images of sample B treated under continuous mode. The left side gives the same image at 10,000 magnification, and the right side shows an image at 50,000 magnification. We found that there are many nanocapsules or nanospheres with regular shape in the coating. We also checked the cross-section of sample B and found out that coatings consist of a layer of polymeric matrix with nanocapsules embedded inside and grafted on the coating. Now let's look at sample E treated under pulsar mode. We can notice there are many particles or many spheres with smaller irregular shape. And that's because in the off time of pulsar mode, the polymerization slows down substantially, while the flow of two aerosols remain unchanged, leading to more irregular deposition. So when we use water aerosol to replace silicon, self-nitrate aerosols, for example F, the coating surface is almost uniform with slight defects. Normally, plasma polymerized HMDS coatings are flat, and the defects can be caused by filaments formally discharged due to the presence of water aerosols into low-cost fragmentation and
We do not hear. We do not hear.
Он есть там вообще?
Доктор Ванг.
У него, может, интернет пропал. Потому что у нас хорошо слышно в зуме.
Увеличение пропало. Внизу под фотографией.
Либо, может, у него завис компьютер.
Хорошо,
напиши в чате. В чате напиши. Ну, тоже банкетная работа.
А я вообще не могу понять, а где вот A, B части есть, а CD частей рисунках я не вижу.
Это значит, у него это связь пропала.
Наверное, они вообще не проявились, вот они снизу должны были быть.
Нет, у него было поперечное сечение. Сначала потом пошел еще добавил слой поперечное сечение покрытое. Вот он, ковыряется.
Доктор Ванг, I see you, but don't hear.
Дома сидит.
О, все сейчас включено.
Can you hear me again?
Okay, we are hearing you. Okay, continue please.
Okay. So let's share my screen again.
I don't see presentation.
Where should I start again?
Just a second. Да.
Okay, I see presentation. You may continue.
From here?
Yes, yes, okay.
No, several slides back.
Okay.
I think several slides back.
Okay.
As I remember, there's sixth slide, as I remember. Yeah.
This one, right. Okay. So here, okay, and simply we can see here the sample, the same image of sample B on the continuous mode. We see quite big nanocapsules or nanospheres in the coating with regular shapes, and we also checked the cross section of coating and found that the nanospheres were embedded in the coating and also grafted on the surface. And we checked the samples on the pulsar mode, like sample E, and we can see smaller nanospheres on the coating. Here we can see sample F on the pulsar mode, but with no silver nitrate in the coating. We only use water aerosols in the experiment, and we found that it's almost flat, but with slight defects. This is sample G, which is deposited with only HMDS, so the coating surface is flat and uniform. And when we checked the EDX of sample B, we found that the coating surfaces, especially when we look at the figure B, this is about the silicon map, and it's almost uniform distributed on the surface, which reveals that the aerosol is also covered by the silicon formed by the polymerized HMDSO. And when we check the EDX map of silver, and we can see the silver is scattered, distributed, which mostly the silver is mostly located in the spherical structures. The observed area also shows that 1% of silver in the coating. So when we check sample E, EDX map of silver presents a quasi-uniform silicon element distribution, and the silver element distribution has a diffuse distribution, which is quite different from sample B. And we can see also the silver content, which is almost 21%. Based on the previous results, we made hypothesized the deposition mechanism of aerosol-assisted plasma deposition. In the first stage, in stage A, before the polymerization, and aerosol droplets containing silver nitrate are transported by helium gas flow into the chamber, while HMDSO aerosols evaporate completely before entering the plasma zone, due to its high volatility and resulting no nanocapsule formation and coating. In the second stage, HMDSO and water vapor are efficiently fragmented, and the polymerization process starts on the substrate as well as on the surface of silver nitrate containing droplets. Meanwhile, silver nitrate aerosol droplets are continuously evaporated and transported to the substrate due to the sedimentation and diffusion. This results in the formation of nanocapsules covered by the polymeric matrix. In the third stage, the polymerization continues on the substrate and the silver nitrate aerosol droplet surface to embed the nanocapsules inside the coating. As the polymerization proceeds, neighboring nanocapsules now grow in size and start to connect and intersect, as seen in some images. We use FTIR to check the functional groups in the coatings. Most coatings give similar functional groups. Only with sample E, we can see weak band from nitrate, which suggests the retention of nitrate in the nanocapsules. XPS gives more information of coating chemistry. In the table 2, we can focus on the silicon and silver. The ratio of silicon to the silver over silicon can serve as an index for relative content of silver in the coating, as we notice that silicon is rather uniformly distributed on the surface according to EDX results. In the pulsar mode, sample E shows a higher silver content than sample B in the continuous mode due to no polymerization in the off time. In the sample FG, almost no silver is found in the coating. Since PD fabrics are widely used in the medical application, we decided to develop the coatings on PD fabrics. For further experiments, we choose pulsar mode to deposit the PD fabrics with 2 regions. The first is the high silver content for antibacterial efficiency. The second is the mild gas temperature for PD fabrics to avoid the melting problems in the deposition. Here I want to mention that this heated accumulation, especially when we choose samples for 10 minutes, if I do the experiments on the continuous mode, I notice that the samples, some samples kind of melt. So for those reasons, I choose the continuous, the pulsar mode to deposit on PD fabrics. And we varied out the flow ratio to flow ratio of HMDSO and silver nitrate in the deposition to check the antibacterial effects as shown in table 3. The antibacterial effects of silver embedded coatings directly dependent on the release of silver ions. We made the release by with ICP-MS. A higher amount of silver release is found on the sample FB1, as we see in the figure. Due to larger flow ratio of silver nitrate aerosols and the thinner barrier layers against the release, which is formed by HMDSO. It's necessary to mention that there is a 2-phase release kinetics for all deposited samples. A fast release of silver is observed on the first day for FP1, FP2, and FP3. Afterwards, a slow release of silver ions. The initial fast release ensures antibacterial protection in the early stage, and which is the most essential stage for infection risk. The initial burst release of silver can be attributed to silver near the surface in the coating, especially for the pulsar mode deposition. Many nanocapsules with thinner shells cannot effectively block the silver ion diffusion into an aqueous environment, while the silver embedded inside the coating and in the capsules with a thick shell can be the reason for the long-term slow release. The release kinetics can be further investigated by the Cosmere-Pepper's model, and we found it's quite a key diffusion. And bacterial effects of the coatings were also examined by E. coli and S. aureus. Both bacteria were incubated with different fabric samples. After 2 days, the colony forming units were counted and their local reduction were calculated. Fabrics FB1, FB2, as we see here, show strong antibacterial properties, which related to more released silver ions, while FB3 shows a moderate antibacterial efficiency. We also noted that the E. coli shows is more sensitive to antibacterial coatings. That's because a thick shell is found for E. coli, which prevents the penetration of cell ions into the cytoplasm and cell lysis. Cytotoxicity was studied through confirmed image, which, as we say here, that the live images, the number of live cells can indicate the viability of cells. As see here, we have 5 samples, and we put all samples incubated with murine fibroblast cells, and there are two control samples, like we see here, A and B, and the cells incubated on the standard protocol using unexploded medium in order to follow the growth of cells, and the cells incubated with untreated PET fabrics are the same condition. Figure B shows that the PET fabric itself does not influence the viability of cells, and FB132 shows that the high toxicity is found to kill all cells. FB3 is the sample FB3 shows low toxicity with still a lot of alive cells, indicating a potential of biocompatible coatings for medical applications. The results from FB4 and FB5 indicates no cytotoxicity of coatings made from HMDSO precursor and a mixture of water aerosols. So to conclude that this APBD technique can be an effective one-step method to produce several ion release controlled coatings. The morphology and the chemical composition of coatings can be tuned by adjusting experimental parameters, and the control release can be achieved by varying HMDSO and several natural aerosol flow ratio. And bacterial coatings on PET fabrics are obtained by optimizing HMDSO, several natural aerosol flow ratio, and the post-mode deposition. And thanks for your attention, and I'm looking forward to your comments.
Thank you, Dr. Wang, for interesting... Yes? Слышно меня? Раз.
Нет, что-то включите.
Раз.
А то, может, выключить?
Сейчас должно...
Вот сейчас.
Раз. Слышно меня?
Да.
Thank you, Dr. Wang, for interesting report. In spite of some technical problems, it's very interesting and good, beautiful reports. Now we have some times for some questions. Have participants any questions? Okay. I want I have some questions. May Dr. Wang, how long is the antibacterial effect of your coatings? How long? Days, weeks, years maybe?
Now I can show you a slide here. We did test for. First, we can look at the iron release curve. We did the test for 21 days.
20 days, да? Yes?
21 days, but we didn't continue our experiment. It takes so much time, and I think it's a good idea to check how long time can the bacterial coatings give good performance.
Oh, okay. Thank you. Have anybody questions? Once more. Okay, I have questions once more. What is the reason for the two-phase nature of the release of silver ions from your coatings?
Yeah. Well. So maybe it's best for me to explain with this hypothetical deposition mechanism. We have with this technique we can devote the core shear structure coatings. So as I mentioned, the two-phase release kinetics, and there's a initial burst release, which we assume that the silver is quickly released from the top surface of the coating, and as you can see here, maybe do you see my cursor there? Or you can see that there are many silver particles. Silver particles, especially for those near the surface, which can be easily released, and this causes the initial burst release. And for the long-term slow release, it's because the silver embedded deep inside the coating. For example, if we look at the figure C, and when you look at this, for example, if you look at the silver deep, very close to the surface of substrate, it's embedded very inside, so it takes more time. It's even harder for them to be released outside. So that's the reason for the long-term slow release.